In this video, we are going to look at differentiating between whether we have discrete or continuous random variables. We're also going to make probability tables for our random variables and then graph probability distributions using spike graphs, which are going to be new, and then also looking at bar graphs, which you're kind of used to. So to begin with, discrete random variable. A random variable that represents the number form of the possible outcomes which could occur for a certain random experiment. So if we're looking at discrete random variables, it's the number of classrooms that have a smartboard. It's the number of students who have a 4.0 GPA. It's the number of broken desks in a room. All you physically have to do is count. If it's discrete, you can physically count and tell me how many are there. Compared to if you have a continuous random variable, you're looking at the GPA of students. The GPA is not a 0, a 1, a 2, a 3, or 4. It's a 3.65, etc. The volume of water in your water bottle, and then just looking at some lengths and things like that. To figure those out, you have to physically measure. There has to be some kind of measurement that takes place to determine what its value is. So we are going to look at specifically discrete random variables. So to begin with, we're going to look at the probability distributions. So for any random variable, there's a corresponding probability distribution. So you can see where each of the probabilities occur, which will take place for each individual value. So here's a quick little example. Let's say we're flipping a coin, and we are looking at the number of heads that occur. So we can say that the probability that x equals 0, the probability that we get 0 heads is a fourth. The probability of getting 1 head is a half. The probability of getting 2 heads is a fourth. And then we can graph that to see what this probability distribution looks like. These are the two different types of graphs you'll see. The left-hand graph we call a spike graph, and the right graph is the bar graph. On the vertical axis is your probabilities. So you can figure out what the total probability is by adding each of them up. So this one is at a fourth, this one's at a half, and this one's at a fourth. Adding all of those up is the certainty that's going to occur, which is 1. Same exact thing works with bar graphs. Only difference is one's wider, one's smaller. Also spike graphs, the 0 is actually on the axis, wherever in the bar graphs the 0 is shifted over. So we'll take a look at a real-world problem with this. So we have a supermarket, and there are 3 checkouts, A, B, and C, and they come and inspect it, and they make sure that weighing scales are accurate. If the weighing scale is accurate, then a Y is recorded. If it's not, an N is recorded. So the random variable that we're going to use is X, and that's the number of accurate weighing scales at the supermarket. So part A asks to list the possible outcomes, and then from there we have to do a few things. So to list all the possible outcomes, we've got register A, we have register B, we have register C. And then over here is the random variable X. And remember, X is the number of working registers, or correct ones. So we could either have a yes for all 3 of them. All 3 of them work. Or the first 2 work and the last one does not. Or the first one works, the second one does not, and the third one works. Or the first one does not, the second one does, and the third one does. Or the first one works, second one doesn't, third one doesn't. First one does not work, second one works, third one doesn't. First one does not, second one does not, third one does. Or does not, does not, does not. So the X is the number of working or accurate weighing scales. So here is a 3, 2, 2, 2, 1, 1, 1, 0. So all of my X values are 0, 1, 2, or 3. So there's part A. So describe using X the events of there being 1 accurate scale. So the X would be, if there's 1 accurate scale, X has to be 1. So the cases would be these 3. At least 1 accurate scale, X would have to be 1, 2, or 3. It's everything but that very last one where it's N, N, N. Okay, so that's just kind of taking a look at what that X value is and how do we represent it. For each random variable, there is always a probability distribution. You'll be able to see where the probabilities take place. The probability of any outcome must be between 0 and 1 inclusive. So it can be 0, which means it is not going to happen. It's impossible to occur. And it can be 1, which means it's certain to occur. So a little notation that you'll see, the probability of event I occurring has to be greater than or equal to 0, but less than or equal to 1. The probabilities of all outcomes has to add up to 1. So if we're looking at every single possible probability, all of them together have to be 1 because something is going to happen, one of those different cases. If we're looking at a discrete random variable, then we can represent it in table form. We can look at it graphically as some kind of picture, or it can be in functional form as a probability mass function p of x. And you'll see one of those in just a minute so you can kind of see what I'm talking about. Table form is what we do a lot just to kind of represent it quickly. Again, it is the probability distribution, but this is kind of a quick way to get yourself there. Graphically is that bar graph, spike graph, and then in function form. A probability distribution provides us with all possible values of the variable and the probabilities of each of those events occurring. So here's our example. We have a magazine store recording the number of sales of magazines purchased by its customers in 1 week. 23% purchased 1 magazine, 38% purchased 2, 21% purchased 3, 13% purchased 4, and 5% purchased 5. What is the random variable? So what are we actually taking a look at? That x value is the number of magazines sold. We're trying to figure out what is it that we're looking at, and it's just the number of magazines that are being sold each time to an individual customer. So in this case, the different numbers that we're using, x can be 1, 2, 3, 4, or 5. So make a probability table for this random variable. So if that's the case, my x values, as I listed, are 1, 2, 3, 4, and 5. The probability of x occurring states in the problem. 1 is 0.23, 2 is 0.38, 3 is 0.21, 4 is 0.13, and 5 is 0.05. So there's my table, and then I can graph this using a spike graph. So starting to set up my spike graph, I have the number of magazines sold, all of my possible x values on the horizontal axis, and then each of the probabilities on the vertical. So I put dots up to the probability, and then I connect with my spikes. And there is the probability distribution using that specific spike graph. The next one that we're going to look at is looking at function form. So here, both A and B here are in function form. So I want to show that the probability is that they are probability distribution functions. If they are, the sum of them has to equal 1. So in the first equation, I have to put 1 in for x, and then 2 in for x, 3 in for x, and 4 in for x. And when I add up each of those individual probabilities, it has to give me 1. So after I calculate each of the individual probabilities, P of 1, P of 2, P of 3, and P of 4, when I add all of those up, the sum of P of each of those individual x values, so x sub I, equals 1. Therefore, it is a probability distribution function. The next one, exactly the same. This one looks a little bit uglier. This deals a little bit more with our binomial distribution, if you can kind of see that. We're taking a look at 0, 1, 2, and 3. So I'm going to come up with each of those individually, and then I'm going to add them up. So setting up each of my equations, 3 choose 0 is 1, etc. Multiplying each of those pieces together, I get 0.064. P of 1 is 0.288. P of 2 is 0.432, and P of 3 is 0.216. Add all those up, I get the certainty that's going to occur. So the sum of all of my probabilities, so the sum of the probability of x sub I occurring equals 1. Therefore, P of x is a probability distribution function. One last example. We've got some marbles. We are doing this without replacement. These are discrete items. X denotes the number of reds that are selected. Find the probability distribution of X. So to begin with, I've got two different cases that are taking place. I'm picking two different marbles. So to start, if I get a red marble initially, there's a 4 out of 6 chance of getting a red marble. Or I can get a blue marble, which is a 2 out of 6 chance. This is without replacement, so now I'm down to 5 marbles. So if I get a red marble the first time, I can get a red marble again, which means now I only have 3 red marbles left out of 5 total. Or I can get a blue one. I still have 2 blue marbles left out of those 5 because I did not replace the first one I picked. However, if I picked a blue marble first, I still have 4 red marbles out of the 5. And to pick another blue again, since I already picked a blue, I only have 1 blue marble left out of the 5. So therefore, all of my possibilities that I have that can occur is a red and a red, which is 4/6 times 3/5. A red and a blue is 4/6 times 2/5. A blue and then a red is 2/6 times 4/5. Or a blue and a blue is 2/6 times 1/5. So I'm looking at X, and X denotes the number of red marbles. So in this first case, X equals 2. In the second one, X equals 1. And the third one, X equals 0. Because again, X is the number of red marbles that you have selected. These are all of my possible probabilities. So if I take each of those products, multiply them together, and then add them, I'm going to get 1. So it shows the distribution of what each of your individual probabilities are, and then adding them up, it has to equal 1. So this is the start, at least, to our discrete probabilities.